So hello everyone. So today we'll see the lecture 5 of the week 1. So in the last lecture we discussed that what is the equivalent representation problem. We discussed the notion of the equivalent representation. We also discussed the notion of algebraic equivalence, the zero state equivalence, and also the relationship between the zero state equivalence and the algebraic equivalent. One of the most important result what we had discussed that time varying state matrix was transformed into a constant matrix, right? So today we will discuss the realization problem of the first. We'll discuss for the LTI systems, and then we will move towards to the LTV case. So first we'll see that how do you what is the problem statement for the realization. So we know that every LTI system can be described by the input-output description given by this one, which is also the zero state response. And if the system is lumped, by lumped I mean to say that the system is having a finite set of state vectors, variables, as well by input state output description, which is given by this one, meaning to say that this representation, when we represent it as y of t as the convolution of gt into ut, it can also be used to describe a distributed system, right? But if we are having a lumped system, then it can be represented also by the state space equation. Okay. So we also know that if the state equation is known, the transfer function matrix can be computed as this one. And this we also had seen in the last lecture about their equivalence, the algebraic equivalence and the zero state equivalence. Okay. Now this realization problem deals with the converse problem. So we know, and in fact we had seen that the computed transfer function matrix is unique in the sense. So try to recall that in the last lecture we discussed at least two different representation of the same system, right? But the transfer function was same for both the representation, meaning to say that their transfer function is unique but not the state space representation. So this realization problem deals with the statement that find a state space equation from a given transfer function. Okay, that let's say some g hat of s is given to us. Now we know that g hat is a unique description of the system. Now for the unique description we need to identify one state space representation, okay, and there could be infinite number of state space representation. Okay, so we need to address the problem of computing the state space equation from a given transfer matrix. So let's define it formally, that a transfer function matrix g hat of psi. So I use this variable xi just to denote that this definition is valid for the continuous time system and for the discrete time system. So in the continuous time we go with the Laplace transform or the Laplace operator s, and in the discrete time system we go with the z transform operator by z. Okay, that the transfer function matrix g hat is said to be realizable whenever there exists a finite dimensional state equation or simply the pair ABCD such that this equation is satisfied. Okay, and we call this ABCD is the realization of g hat of s or psi. Okay. So we have already discussed that g hat of psi could have infinite number of realization in the sense that there could be infinite number of the pair ABCD. So this problem is fairly complex, that among all those representation, which representation is to choose or how to ensure that there exists a representation, right? So in this topic we will study the realizability condition and we compute only one realization. So given a transfer function matrix, we will study those conditions under which we can say that this transfer function is realizable, and with respect to that we compute one ad hoc realization. Okay. So this is the most important result, that a transfer function matrix G hat is realizable if and only if G hat of S is a proper rational matrix. So in fact this point we also mentioned in the beginning of this week 1 when we were discussing about the causality and all. Okay. So the proof of this result is quite long, and we will give the proof in two different parts, which first we call the necessary part and the sufficient part. So in the necessary part, that if G hat is realizable, then G hat is a proper rational matrix. Basically we also denote it by this symbol, meaning to say that the realizability of G hat of S implies that G hat is a proper rational matrix. Okay. The sufficient part, which is the converse of this part, that if G hat of S is a proper rational matrix, then your G hat of S is realizable. If this necessary and sufficient condition is satisfied, then the realizability of G hat of S is basically equivalent to saying that G hat is a proper rational matrix. Okay, so let's see the necessary part. So we already assume that G hat of S is realizable. So if G hat is realizable, then we can write it by this part. Okay, let's denote this G hat underscore SP, where I have not included the D matrix. So without the D matrix, we know that define the transfer function. Okay, and this transfer function we call it the SP, and we know that I can define this the inverse of Si minus A by the ratio of adjoint Si minus A transpose divided by the determinant of Si minus A. Since it is a polynomial, I can commute. Okay. Now note here that if A is a n cross n matrix, then the determinant of Si minus A would have the degree of the characteristic polynomial equal to n. Right? We also discussed in one of the previous lecture that the degree of this adjoint of Si minus A would be at most n minus 1. Okay. So we know that this part, Si minus A inverse B, is a strictly proper part. This is the reason we defined it as SP, which implies the strictly proper part. Now if the D matrix is a non-zero matrix, then this whole part is basically the proper. So this shows the proof of the necessary part, that if G hat is realizable, which we started from here, then G hat of S is a proper rational matrix, and we arrive to the conclusion that G hat is a proper rational matrix. The sufficient part, which is the converse. So we show the converse, that is, if G hat is a Q cross P proper rational matrix, then there exists a realization. Meaning to say, if there exists a realization, then that transfer function is realizable. Okay. So let's see. So first of all, we decompose the transfer function G hat as the summation of G hat infinity plus the strictly proper part of the G hat, and we know that this G hat is basically nothing but the D matrix. Okay. Let's define this polynomial, this D of S, whose order or degree is R, which is basically the least common denominator of all the entries of this strictly proper part of the transfer function. Okay. Then I can express this GSP as the ratio of 1 by ds, because D of S is a polynomial and this is basically a matrix which is n, the function n of s, and this n of s is basically given by this long part where we have r number of constant matrices of dimension q cross p. Okay, and all these s are the scalars. So let's say if you want to visualize, let's say I have a 2 by 2 system. Okay, so this 2 by 2 system I can represent by y1 by 2 equal, let's say g11, g12, g21 and g22. Okay, let's say we have this 2 by 2 system, and these all these g11, g12, g21 and g22 are the transfer function, basically the ratio of polynomials, right? Now this I can express this let's denote this gi, gij, let's say some polynomial ij and some denominator polynomial ij of s. Okay, so this, after taking the LCD of all the elements of this transfer function matrix, I can express this transfer function matrix as, let's say, some LCD of this matrix 1 by ds, and this would be a matrix in the sense n11 of s, n12 of s, like this. So the same has been expressed in this form. Okay, because all these nij would be the function of s, and I can take the n matrix common, and finally all these ni's would be the constant matrix of dimension q cross p. Okay, so now we give a set of equation given by this A matrix, this B matrix, this C matrix and this D matrix, and we claim that this set of equations is a realization of the transfer function g hat of s. Okay, where all these IP are the identity matrix of dimension P. All these zeros are also the matrices having its elements, all its elements 0. This A matrix is having a dimension of RP into RP. Okay, so note that here it's that what the point what we had raised earlier, that there could be infinitely number of state space representation, and it is not necessary that all these representation would be having the same dimension, right? So here we would be having this the A matrix of dimension RP into RP, B RP into RP, and C Q into RP. In overall it would give me the transfer function of dimension Q cross P. You can verify by yourself these dimension of these matrices, because we have R number of elements of P matrices, which are the block matrices. So in overall it would give me this this dimension. Okay, so now we need to show that this set of this state space representation is a realization. If we are able to show this, meaning to say that g hat of s is realizable transfer function. So let's see. So first of all we define this z as z1 to zr equal to s, the inverse of si minus a into b. Okay, where all these zi are the p cross p matrix. So if all these zi's are the p cross p matrix, the dimension of this matrix capital Z would be rp into rp, because we have r number of elements of matrices p cross p. Okay. So if I write the transfer function of the state space representation, what we had introduced earlier, which in general way I can represent by this, is given by this, where I have replaced all these si minus a inverse b by their z1 to zr. Okay, you can write it more explicitly to finally arrive to this equation, right? this equation, I can also write it Si minus A into Z is equal to B by taking this part or pre-multiplying both side by Si minus A. Okay, Si minus A Z into B or Sz is equal to Az plus B. So let's see this part. Sz is equal to Az plus B, where now I have explicitly written this Z matrix starting from Z1 to Zr. We have this A matrix into Z plus B matrix of the state space equation what we had introduced. So see from starting from the second element to the last element. So if you notice, we have Z2 is equal to, or S into Z2 is equivalent to IP into Z1. So this is this part, that S times Z2 is equal to Z1. If we see the third element, which is S times Z3 is equal to IP times Z2, where I is an identity matrix, and so forth and so on. If we keep on continuing, it would be S into Zr is equal to IP times Zr minus 1. Okay, because all these elements are 0. Now from here, we compute this, we can write Z2 as Z1 by S, Z3 as Z2 by S, and then replacing Z2 by Z1 by S, we can parameterize all these Z in terms of Z and the degrees of S. And after replacing all these putting all these Z's into the first equation, which is S times Z1 is equal to this into this plus this into this plus IP. This is the part. And replacing all this Z2 to Zr by these equations, in fact we have parameterized this whole equation in terms of Z1 only. You can write this equation by yourself as well to visualize that how we have arrived to this part. Now, using the definition of D of S, what we have introduced, I can write this last part. If you pay attention to this one, this part, so this part, I am trying to simplify it in the next slide by this one. So I can write it as the ratio of the polynomial D of S divided by the S of power R minus 1 into Z1 is equal to IP. Okay. So once I have defined Z1, which is S to the power R minus 1 divided by D of S into IP, I can compute all these, the remaining Z's, which were parameterized in terms of Z1. Okay. Now substituting all these Z's into the original equation, if you see here, this part from where we started. So after putting here, I get the original transfer function of the state space system, meaning to say that the set of equations what we have introduced is one of the realization of the transfer function. Okay, this proves the sufficiency part. So we are now sure that the realization of the G hat of S is basically equivalent to saying that G hat of S should be a proper rational matrix. Okay. Moving on to the LTV systems. So we know that we cannot use the Laplace transform tool for the two basic reasons what we have introduced in the one of the previous lectures. So the input output description is given by this, and the input state output state description is given by this. Again recalling the same problem, that if the state equation is available, the impulse response can be computed from this one, where this part is basically the state transition matrix, the solution of the state transition matrix in terms of the fundamental matrix. Okay. Again we want to answer the reverse problem, that given a transfer function, I want to compute the pair ABCD, all the time varying parameters. So this is the result for the LTV system, that given a Q cross P impulse response matrix GT comma tau, we say that it is realizable if and only if that matrix can be decomposed by this, where M and D are respectively the matrices of appropriate dimensions. Now that this result says that if any transfer function matrix is the transfer or the impulse response matrix, I cannot use the word transfer function because for the LTV systems we don't have the transfer functions. So for given impulse response matrix GT comma tau, we say that there exist ABCD matrices. If the given response matrix can be decomposed into this part. Again, we will be doing this, the proof of this result into two parts. One is the necessary part, another is the sufficiency part. That if GT comma tau is realizable, then there exists a realization that satisfies this one. This was the idea of introducing here. Because if it is realizable or the state equation is available, then I can express the impulse response matrix by using the parameters of that state equation, meaning to say that there exist some parameters. So there exists a realization that satisfies this equation where X is the fundamental matrix, and the sufficiency speaks about that if GT comma tau can be decomposed as this, then the response matrix is realizable. Okay, both ways, this way and similarly this way. Okay, so let's see the proof of the necessary part. So this proof is pretty much straightforward. That pay attention to here this the response matrix. So if we denote this Cx by M and this part as N, right? So we have in fact already decomposed the transfer function in terms of the required result, meaning to say that GT comma tau is realizable, then there exists a realization that satisfies this part. Okay, so MT and N tau, we can replace this and this satisfies the necessary part of the theorem. Okay, the sufficiency part, that if G, the impulse response matrix, is decomposed as mentioned above, then it is realizable. We have the proof of this one, that if GT comma tau can be decomposed as above, then the n-dimensional state equation is given by this. Okay, so here we are introducing a state space representation of the time varying matrix. Note that the state matrix is 0. There is no matrix which is being multiplied by the state variable. So we have x dot is equal to n of t into u, and the output equation is given by m of t into x plus d of t into u. So if we compute the fundamental matrix of this one, we already know that the fundamental matrix is an identity matrix, right? And thus the impulse response, if I compute the impulse response of this one, is given by finally the impulse response matrix, which proves the sufficiency part of this theorem, meaning to say that decomposing, so if we go to the result, that decomposing the given impulse response matrix into this form is equivalent to saying that the response matrix is realizable, meaning to say that there exists the pair ABCD. Okay, so here we conclude the theoretical part of the first week. So in the next lecture we will see the some tutorial problems.